Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into the Chapter 6 review in the Big Ideas Math Integrated Math 1 textbook. This is on exponential functions and sequences. How little I even forget as I talk about these things. I've been focusing so much on exponential, and yet the end of the chapter was really all sequence-based. There were exponents, and with geometric sequences, you'll have them, but there were also a lot of things on arithmetic sequences, and they really talked about them a lot. So how little I forget that the chapter is called Exponential Functions and Sequences. That's really the highlight of the end half of the chapter as a whole. The beginning half of the chapter had a lot of things on exponential functions, compared them to linear to remember how we're going to do things. So we have arithmetic sequences tackled pretty well, hunkered down pretty well. So we have 33 problems to do as a review. There are some examples along the way of each individual section. Find the PDF down below with this stuff and graph paper and all that kind of stuff we're going to be using. I think I'm going to use both sets of graph paper, the tall graph paper and the square scaled graph paper, as well as the timestamps for each problem in the problem set. Without further ado, I'm going to go ahead and get started. We have section 6.1 on exponential functions. They make a table of values with this 9 times 3 to the x power. First thing I'm just going to note is you can't do 9 times 3 first in this. 3 must be raised to the x power by order of operations, even when you substitute these x values in. Now, I plan on not officially using a table, but I can use the concept of what they have with tables, such as 9 is the y-intercept. It's the value of y when x equals 0. And that's not always the case if there are certain shifts, but 9 is very important with respect to when the exponent is 0, and that's when x is 0 in this case. The 3 is your growth factor. The 3 signifies what you're multiplying by each time that you increase x by 1 here, so times 3, etc. And that's really what I'm going to be working off of here, minus some translations. I'll talk more about asymptote and such later, but this has a horizontal asymptote on the x-axis because you can never get a y value of 0. Note that if you keep dividing by 3, if I multiply by 3 going to the right, then I divide by 3 going to the left. Well, 1 divided by 3 is a third, and a third of a third is a ninth, and 1 over 27, 1 over 81. You can see it gets really close to 0, but never hits and never becomes negative. So it gets closer and closer to that line, and this line will shift based on our k value. So they draw a smooth curve. They draw their arrows because there are points that go throughout there. So we have numbers 1, 2, and 3 where we are going to graph the function. We're also going to describe the domain and range, something which they didn't do on these particular problems. So let me get that one started here. Number 1, we have f of x equals negative 4 times 1/4 to the x power. So no translations that I see. This thing is straight up as if you use that a and that b exactly as I mentioned in the previous problem. I am going to begin with that horizontal asymptote. It's something that I don't think they ever used that word, that term, that phrase here in this chapter. They'll use it, I guess, in IM2 or at least IM3. But asymptote, it's that line we do not touch or cross. And I use that as a feature so I know where to plot my points. Negative 4. Let me actually bring this thing up. Negative 4 is our y-intercept. So this will be a negative function, a negative exponential function, and it has negative decay. 1/4 is what we're multiplying by. That's the same as dividing by 4. Negative 4 divided by 4 is negative 1. And that times 1/4 is negative 1/4 and negative 1/16. So that's the idea of table usage there without actually using the table. If I multiply by 1/4 going this way, then I divide by 1/4 going that way. Same thing as multiplying by 4. Negative 4 times 4 is negative 16, and negative 16 goes way down here. And here's the idea of this exponential function. It's actually something, I mentioned it before, but it's called negative exponential decay. As x increases, the y values, well, they technically increase because they get closer to positive, but they're getting closer to 0. So smaller negatives are coming out as a result. That's what I call decay. Numbers that are getting closer to the asymptote, closer to 0. They have that shrinkage. We could consider as it goes to the left, it's growing negatively, right? But if they're asking what is it doing as it's growing to the right, as x goes to the right. And it's decaying. So negative exponential decay, this domain is indeed all real numbers. You can hit any x value you'd like and get a y value. As far as the y values, though, you're limited to only negative numbers. It never even hits 0. Y is less than 0 is our set there. And that is number 1. Number 2 has a couple new features in mind. One of them is a missing value of sorts. Let's talk about that. And then the other is a translation. So as far as the missing value, you saw in this one, there's something multiplied by something in parentheses. This is y equals ab to the x power. Well, the a is missing here. If there's a b there, your a is 1. in this case. Now that would kind of represent that y-intercept value, except there is also a translation. There is a shift of sorts. Now that is your x minus h. If I were to write this thing in full, it would be like a y equals a times b to the x minus h plus k. This is a horizontal translation, and it's opposite of what you see here. Basically, I have to substitute -2 for x to get 0 for y, which is an important value that wipes out the b value, where 3 is not yet in use. But let's first draw that horizontal asymptote. There's no shift on this thing vertically, just horizontally, and we are going to shift 2 units to the left. This x plus 2 means everything's going to be 2 units to the left of what it was before. Remember what I said a was going to be 1? So instead of being a y-intercept right here, go 2 units to the left, and boom, there's that a value. If you'd like to plug in -2 and figure out how that works, -2 plus 2 is 0, 3 to the 0 is 1, and 1 times 1 is 1. So when x is -2, y is 1, boom. After that, we use the b value here, this 3, to signify what you multiply by each time x increases by 1. So 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. I can't fit it, probably somewhere way up there, can't fit it. That's as far as I can go. And I can divide by 3 going this way, where I get basically 1/3 and 1/9 and 1 over 27 and really close to 0 without actually hitting it. So we are a positive growth function this time. Also exponential, asymptote still on the x-axis. And we have this graph here. You notice I tend to draw half arrows on this side to just state I'm going forever left, and it's technically going down, but closer and closer to 0. Never hits, never crosses. That's my version of sketching that one. My domain is, once again, all real numbers. You should see a change on that, as long as it's not a word problem. And the range this time, we are above 0, greater than 0, positive values. Number 3, we have the same thing when it comes to a. The missing a value means the a is 1. Keep that in mind for this problem. But there is an h, there is a k. We have a couple things going on that front. This is 2 to the x minus 4 power minus 3. Once again, the a value is 1. I'm not going to actually write it. Let's just keep that in mind when it comes to what we do. And that will be where my first reference point comes from, given the translations that we have. And we have translations. We have a horizontal and a vertical. Remember when I said horizontal is on the x-axis? Not anymore. Now we shift 3 units down. So -3. 1, 2, 3. If I start with my asymptote here, then I can graph everything in relation to my asymptote, which means I don't have to subtract 3 to anything anymore if I say, this is my new x-axis, right? This is where I start from. So let's do that. Keep in mind that a is 1. How far up or down we go from the asymptote, based on what a is, based on our shift. This -4 means we are actually going to shift 4 to the right to feature being 1 above the asymptote right here. So this is actually a point on the graph. Try and plug in 4 for x, see what you get for y. You should get -2. From here, everything's based on this 2, right? If that was that 1, the b is the 2. That's what we multiply by as x increases. 1 times 2 is 2. 2 times 2 is 4. Now notice what I'm doing. Distance from asymptote. Not y value and not distance from the previous point. 1 away, 2 away, 4 away. 8 away is at y equals 5. That's 8 away from -3. You're going to get a lot of points off this one. 16 away from here is 13 up, like that. So that's 16 away. And I can't fit anything beyond that. Let's go to the left and divide by 2. Let's get half, and a quarter, and an eighth. I like getting a lot of points like that one to really hit home that, wow, if I used a table, that would have taken a long time to get all those values. If I understand what I'm doing with this function as far as its growth, then I can get this done a lot faster. And trust me, when we do the chapter test, if they're as easy as these kinds of problems go, I'm going to go super fast. Less teaching, more doing when I hit the chapter test, right? Domain, all real numbers. Range, we are above a value, but it's not just 0 this time. We're above -3. You'll never hit -3. You'll never be below -3. You're always above -3. Every y value in existence there. There's number 1 through 3. Number 4 says, write and graph an exponential function f represented by the table, then compare the graph to the graph of g of x equals 1/2 to the x power. So they state graph just based on the table itself. I suppose I should just copy and paste that one. And let's come up with an equation based off this. Now, everything I mentioned before can help you with that. I'm trying to decide. Let's get the equation first. It says write first, so let's do that. We can come up with an equation based off 2 concepts. The y-intercept, which is the value of y1x equals 0, that's our a value. This is assuming, guys, they're doing just y equals ab to the x power, or f of x equals ab to the x power. No translations and such. Because you can make a translated version of this, at least horizontally. Vertically, I think this is getting closer and closer to 0, so I don't think there's a plus k. But this is your a value. Your b value is based off what we're multiplying by going from one value to the next. And now that we finished the chapter, you've done a lot on geometric sequences. So think of it like a sequence. 2 times what is 1? 1 times what? What's your common ratio? You got to do this divided by this to figure it out. This divided by this, or this divided by this. I think this is the easiest one. 1 over 2, it's 1/2. It's 1/2. Your b is 1/2. That's what we're multiplying by each time. So as far as an equation goes, it would be f of x equals 2 times 1/2 to the x power. Boom, just like that. Now we're still going to graph the thing. There aren't many points on that one. I can get you more points on this one if you'd like. So for this one here, we can just go, let's just get all of them, right? Let's draw the asymptote. Let's go, we have a y-intercept here at 2. That's the a value, right? A is 2, and then times 1/2 is 1. Times 1/2 is 1/2. Times 1/2 is 1/4 and 1/8. And then divide by 1/2 as we go this way. So divide by 1/2 is times 2. Because half of 4 is 2, right? So double 2 is 4. Double that is 8. Double that is 16. And we're going that way. So this is positive exponential decay. It's decay as this thing goes down this way. Closer to the asymptote, smaller positive numbers as x increases. Okay. They said compare it to g of x equals 1/2 to the x power. Now g of x equals 1/2 to the x power basically has an a value here of 1. So the difference is this thing is at 1 when this is at 2. This is at 1/2 when this is at 1. This is at 1/4 when this is at 1/2. It's always half of what the other one is at any point in time. So here, 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 etc. You could consider this one of two ways. You could almost say, hey, if we move everything 1 to the left, we would get that same set. That's true, but when you look at just the equation itself, we don't really want to talk about it that way. See, that's why I said there are two different forms from the previous problem of which we could write. No, was it this problem? It was this problem where I said we could write the equation a couple different ways. So based off this one, you might say it's a different y-intercept. Okay. You might also say, hey, this thing's just shifted. Just shift it 1 to the left or whatever, right? Okay, there's that. Hold on, let me drink some water first. But when we've spoken on a before, when we're multiplying by something to change y, the true nature kind of answer we want to tend to say is about a vertical stretch. Compare to the graph of g of x. The graph of f is vertically stretched by a factor of 2 from g. Now, based on the points that you see, would it be wrong to say the graph of f is a translation 1 unit right from g? That would not be wrong. But we didn't write this equation in that way. It's possible. It's possible to write this equation as 1/2 to the x minus 1. It's possible for us to do that as well. Shift everything 1 to the right and do that same thing. These are actually the same graph, strangely enough. Are we going to do that? No, let's do it based off the y-intercept and use it this way. I think I still need water. Let me take another sip. Hang on. Okay. Let's go to section 6.2. Now, section 6.2 was on exponential growth and decay. A lot less graphs. I don't think we'll really have any. And we're using something based off this equation-ish. We're going to have a different letter than x and a different set than b to represent what we're talking about with respect to, literally, growth and decay. So let's look at the example that they have and see what they want to talk about with it, okay? Determine whether 2 times 1.13 to the t power represents exponential growth or decay. Identify the percent rate of change. So now we're going to speak a lot more on decimals to use percentages. Okay, so be comfortable with the decimal instead of like 1/2, we'll say 0.5, things like that. Now 1.13 is a number that's more than 1. You would literally have to add something to 1 to get what that is. That does make this exponential growth because multiplying by 1 keeps a number the same. Multiplying by a number more than 1, even in a decimal amount more than 1, will make it grow as t increases, as time goes on. It's your new x. So the function is in the form y equals a times 1 plus r to the t power. Plus r, not minus r. There will be minus r examples. Now r will represent our percent change in decimal form. So we can find out what r is based off subtracting 1 from here, right? 1 plus what is 1.13? Well, 0.13. 0.13 represents the percentage growth. It's actually 13% growth. Growth because we're adding to 1, 13%. That's a decimal shift 2 places over to the right from the decimal that we have. That's all they have for that example. They can do a full word problem set. I'm anticipating that in a moment. We're doing numbers 5 through 11 right here. Determine whether the table represents exponential growth, decay, or neither, and explain. Now, growth is as you would, well, a couple things. We just did some graphs, and I think we did a graph on, we didn't do negative growth, but we did do negative decay. We won't have any negative graphs here as far as I'm concerned. Everything's going to be, y values will be positive. So when the numbers go up, you're thinking growth, as in it's not going to be decay. And you're right, it's not going to be decay, assuming the x's are increasing constantly. Yes, x's are increasing constantly as x's add 1 each time here. The real question is, are y's changing by a constant ratio? Not a common difference, but a constant ratio. And here we're doubling, doubling. It sounds like the common ratio thing from geometric sequences. Is this a geometric sequence? Sort of. Yes, this is an exponential function because as x increases by 1, y is multiplied by 2. I should probably type these ones. As x increases by 1, y is multiplied by 2. I'll do that probably for the next ones moving forward. So there's number 5. Number 6, let's get that table ready. We have to represent either growth, decay, or neither. Now, a neither case would pretty much just be that it doesn't have a common multiplier for y as x increases by a constant amount. So that's something to check on. Now, this one, if anything, would be decay, given that the numbers are shrinking. The positive numbers are shrinking. X is increasing by 1 once again. The question is, are we multiplying? And it is a multiplication question. Are we multiplying by something over and over from here to here? That's what I want to check on. I want to check on this b value, basically. What is 108 over 162? And we can check in either decimal form or fraction form. I'm good either way. 72 over 108 or 48 over 72. Are these all the same is the question. Now, if I used my calculator, there's a way to reduce these fractions if you divide by certain numbers. But if I use my calculator, I can check 108 over 162, and I believe it's, 2/3. Hold on, I have to reset my calculator. All right, 108 over 162. I think it's going to be the 0.6 repeating, that number. And then we'll try 72 over 108, which I think is also 2/3. And this other one's also 2/3, 48 over 72. So this is what we're multiplying by each time. By the way, that fraction equivalent is indeed 2/3. So that is what we're multiplying by each time. I mean, I would prefer you tried fraction reduction, divide these by 54, divide these by 36, divide these by 24. You do get 2/3 for each of them because of that constant rate. This is exponential, but it's decay. Oh, I'm sorry. I said exponential. I didn't say exponential growth here. Exponential growth. This here's exponential decay. As x increases by 1. By 1 is just a constant amount. Y is multiplied by 2/3. Try not to say what it's dividing by, okay? That's the important part there. Okay. Now, there was no neither case. I assume we might run into actually some form of a neither case when we talk about sequences. Is it arithmetic, geometric, or neither? So get ready for a test where nothing pans out in that way. Number 7 through 9 is like the example question. And this says y equals 0.99 to the t power. Now, they showed you a form of an equation up above earlier that said y equals a times 1 plus r to the t. I want to note 2 things on this. Number 1, you could also do minus 1 minus r to the t power. And that's exactly what this one's going to be here, because the 0.99, we're subtracting something from 1 as the number smaller than 1. And number 2, just like the exponential equations from before, we have an a value. It's just missing. It's 1. The a actually has nothing to do with whether this is growth or decay. It's all about the 0.99, but I want you to make sure that you know which number is representing what. So as far as this one goes, this equation could also be written as y equals 1 minus 0.01 to the t power. If you're trying to figure out your 1 minus r in this case, your r, subtracting, is 0.01 to get 0.99. That's what r is. R is 0.01. It is being subtracted. That makes this thing a 1%. That is 1% decay. 1% decrease, 1% decay. It says identify, let's see, exponential growth or decay, 1% decay. I'm just answering both things together. I hope that's okay. All right, there's number 7. Let's go to number 8. F of t equals 6 times 0.84 to the t power. Doesn't matter that it says f of t versus y, that's fine. Doesn't matter that this says 6 versus any other number. It's all about that 0.84, baby. Now, this time I'll write it a little bit differently if it's not so obvious to you. This is, once again, a 1 minus r, but that is 0.84. And we need to solve for r. You add r to both sides, you subtract 1, you do 1 minus 0.84 from both sides, and you get an r value of 0.16. So that's where it comes from, right? But it is a minus. So this does mean it's a 16% decay. Decay rate of 16%, that's what happens. So your numbers shrink every time that t increases by 1. They shrink 16%. Number 9 is more like the example one because this is growth. You can tell that this one's growth because we are adding something to 1. These are probably easier for you to calculate. 1 plus what is 1.05? Well, 0.05. 0.05 represents 5%, not 50%. And because it's increasing, this is a growth. So 5% growth on this one. Exponential, by the way. These are our exponential growth and decay. All right, numbers 10 and 11 appear to be word problems using this format. So we might have to set up the entire equation from here. Here we go. Oh, there's more to state on this one even. You deposit $750 in a savings account that earns 5% annual interest compounded quarterly. Write a function that represents the balance after t years, and then what is the balance account after 4 years? So 2 different parts. First of all, the equation that we're using looks like this here. It's a form of what we were using before, only, oh, it's on the other page. Oh, I think they used the letter y here. It doesn't matter. YA, it's the final amount, the accrued amount after a certain amount of interest. The difference is we have this n value now involved. Instead of 1 plus r, it's 1 plus r over n into the n times t. There are several differences here. First of all, we'll never have a minus with interest. T is always represented in years, and n is the number of times that you compound that interest during the year. If it said annually, then n is 1. And if n is 1, then it's like it doesn't exist. But this says compounded quarterly. So when I'm setting up all the information, our p-value is our principal interest, that just like the initial a that we had before, $750. Your percentage is 5%. We just saw that that is 0.05. Good on the book to transition from one to the other if you notice it. You should never write 0.5 as a result like I almost did. Compounded quarterly, n is 4. So these are the bits of information that we can do to write out part A, the model. A equals, or y equals, I'm used to writing A equals, forgive me. A equals 750 times 1 plus 0.05 over 4 to the 4 times t power. Now we can clean this up slightly, that inside part. 0.05 over 4 is 0.0125. So when you add that to 1, that's 1.0125 to the 4t power. This is our model we're going to be using based off the t years. So part B says, what is the balance after 4 years? This is where we do t equals 4. So before we use these to get part A, now for part B, if t equals 4, let's find out basically A of 4. 750 times 1.0125 to the 4 times 4 power. Now I'm going to write that as 16 straight up. I don't want to make a mistake on doing something in the calculator, and we will use the calculator. I don't want to make a mistake on using that portion of this as we mosey on forward. 750, just type it exactly as it's written in this case. Boom, 16. If I wrote 4 times 4 up here, it might just raise it to the 4th power and then take the whole result of that thing and multiply that by 4, which is not the same as this answer. This answer is, this is money, by the way. So 914.917, etc. I'll go to the nearest cent. That's what we can do with money, 2 decimal places. So I'll do 92 cents, $914.92. Like that. That's our accrued amount. If you put y equals whatever, that's fine. It's your final amount. Okay, number 11. The value of a TV is $1,500. Its value decreases by 14% each year. Notice decrease. Write a function that represents the y value after t years. What's the value of the TV after 3 years? Round to the nearest dollar, not nearest cent. I'd actually argue this question's easier. We go back to our y equals a. See, the letters don't really matter, guys. It's just the formula that we've seen. But 1 minus r to the t power. Notice it is a minus because it's a decay. And it's not compounded over time or anything. It's just this. So our a value is the initial $1,500. It's going to decrease by 14% each year. That's r, 0.14. So these two together, we can make an equation out of it that says y equals 1,500 times 1 minus 0.14 to the t. And please simplify that. This is part A, by the way. This is y equals 1,500 times 0.86 to the t power. Now, did we have 0.86 as a number before? Oh, that was 0.84. Never mind. Very, very close. Okay, that's part A. And part B now asks, how about after 3 years? If it's decreasing by this amount each year. By the way, be very careful. Make sure that it did say years. It did. So our t equals 3 will be what we're substituting here. If this said each month it decreased 14%, which is a crazy amount that it would decrease over time, then you would actually do 36. 36 months later is 3 years. Anyway, we're not doing that. I'm just calling attention to it because the review didn't do a problem like that, it seems. So when we multiply this one here, or input it in the calculator, we're going to get a number less than 1,500. I don't know exactly how much. I'm going to venture a guess around $800. I don't know. 1,500 times 0.86 to the third power. 954.084. They said to the nearest dollar is around $954. So y is about 954. Like so. Okay. And that is section 6.2. Let's move to section 6.3. We compared linear and exponential functions. Maybe this is where... Not quite. I was going to say if this example said linear, exponential, or neither, I was going to say maybe we can check some out. But hey, some won't be exponential. Some will be linear. So let's take a look at the example they have before we do these 3 problems. Tell whether each table values represents linear or exponential function, then write the function. We notice on these x increases by a constant amount, in this case 1. As x increases by 1, what is y doing? Here we're seeing a separation of a difference of 5. You're adding 5 each time from one number to the next. Something you have to test for. But if it calls attention to you, go for it. As we're going from negative to positive like that, most exponential functions won't be doing something like that. Sounds linear. Y is increasing by 5 as x increases by 1. That's a linear function. This one, x increases by 1, and y is doubling its output each time. So this will be an exponential function, exponential growth. They do say write the function as well. Now, writing the function, we just did one for y previously based off the y-intercept and, of course, the growth factor. So the y-intercept is 20, the growth factor is 2. That's something that I'm going to be, they're saying the same thing, y-intercept, etc. So clearly they have something in mind the same way that I do with respect to y equals ab to the x power, how you could use it to feature the equation, and how I've used it to graph without a table. Anyway, in the these ones right here, don't forget y equals mx plus b. Your y-intercept still exists in this one, 0, negative 1. That's your b value. And your slope is how much you rise as x increases by 1. Up 5 over 1, your slope is 5. So y equals 5x minus 1 is that equation. Okay, let's go to our problems. We're going to do the same thing on numbers 12 and 13. So let me copy this over. They say use this table to determine is it an exponential function or a linear function, and then write the equation as a result of it. So the first one shows a staggering decrease on y, but then it slows up its rate. That means it's likely not linear and it's likely exponential. So we got to figure out what's happening to y each time x increases by 1. That's the true blue goal here. So we got to do some number divided by another one. Knowing that it is exponential, right, it's clearly not linear and neither is not an option. So knowing that it's exponential, let's take the 2 easiest ones to divide that you can. Let's do 6 over 24. And yes, you go in that way. So it's 1/4. 1/4 is what we're multiplying by each time here. It means the same thing as dividing by 4, but we mentioned what we're multiplying by. So this is an exponential function. I might have to sneeze here in a moment. Tell in the future. It's an exponential function. The a value will be your y-intercept, 96, something I don't want to graph, and thankfully I don't have to. So the y-intercept is the value of y when x equals 0, that's a. Your b value is that 1/4, and it looks like that. This is our function, y'all. So y equals 96 times 1/4 to the x power. Number 13, probably linear, otherwise we don't get our chance at doing both, but let's see. Yep, looks linear to me. So number 13, we have a constant decrease as x increases by 1, and that's what's happening. I wish they had one as x increased by 2 or something, so we could make sure that we reference that for our slope. But as x increases by 1, your y's are subtracting, well, 16. And you can try that with any, 16 minus 16 clearly gives it away to be 0. But subtracting 16 each time, this is a linear function. Linear function, let's use y equals mx plus b to write our equation. Our b value is our y-intercept, so that'll be this guy here, when x is 0. Not when y is 0, that's your x-intercept. So there's your y-intercept, b. Your slope is down 16 over 1, right? You divide this by that. That's why I said if this was like 2, then your slope is -8, not -16. But that's not the case. So your slope is -16. Your y-intercept is +16, interestingly enough. So your equation is y equals -16x plus 16. That's our linear function. Okay. Number 14. The balance, y in dollars, of your savings account after t years is represented by boom. So they give us the model of the equation this time. Maybe we have to decipher what all this means. Let's see. Oh, I forgot. This is a section where we're comparing a linear to exponential model. That's right. The beginning balance of your friend's account is $340, and the balance increases by $10 each year. Is t in years for... Yeah, t is years for this one. So this is me, I guess. This is friend. So friend can be... It's linear. It starts at 340, and they increase $10 each year. So like this. We have one and the other. So me or you, however you want to call it, me and friend. Friend. Free end. Okay. Compare the account balances by calculating and interpreting the average rates of change from t equals 2 to t equals 6. Predict which account will have a greater balance after 10 years. Explain. Now they said predict, so I make an early prediction. We probably calculate afterward. So here's the thing. Let's talk about friend first when it comes to average rate of change. Now average rate of change for us really means slope. In this case, the slope is always 10. So slope of friend, I'll put M of MF, is 10. So that's $10 per year on average from year 2 to 6. From any year, really, that's going to be the case. For me, it's going to be a little bit different. For me, what I have to do, the slope of me from years 2 to 6, I have to find out what we get from... You know, I really want to use f of x, g of x, things like that. But anyway, I have to substitute 2 and 6 for t and figure out the dollar amounts that I have, right? It's going to be some sort of y2 minus y1, how much money I have in those years, over x2 minus x1. The thing about mine does not have a slope. I'm an exponential function. This average rate of change will be the slope over that time, so we have to figure out how much money I'm increasing per year on average over that time. So that's the calculation I have to do. And I'm going to use the calculator for that. I can use it straight up, but what I'm going to do is more so get those dollar amounts so you can see exactly what it is that I'm referring to rather than just the final answer. So there's a dollar amount here. I'm going to round it, not in my calculations, but just in what I write so you understand what it is we're talking about. So 300 times 1.05 squared as well. So what we're doing is basically finding this difference here. Give me a second so I can write it. 402 minus 330.75 all over 4. What I'm doing here is I'm finding the difference between how much money I made on year 2 and how much money I made on year 6. This is about $72. And when you divide it by 4, well, it's about $18, right? So I'm going to use this whole calculation thing here. I'm going to do 1 minus the other. This minus 300 times 1.05 to the second power. And then divide that by 4. And then you get around that 17.82, I'll say. $17.82. So it's an average of $17.82 per year in that time frame from years 2 to 6. Okay? So, they say predict which account will have a greater balance after 10 years. Explain. Well, here's the thing. I start with $300. My friend starts with $340. They started with more. From years 2 to 6, I'm already seeing a greater average than my friend. That already means on year 6, my thing is even significantly more rate of change than that. And it's only going to climb the next 4 years. Despite the fact that I start $40 less, I believe that even the $17.82 on average for the next 4 years, it doesn't quite offset the 40, but everything after that, I believe, will offset that 40. I believe that I already have, we probably have about the same amount after 6 years, actually. I probably have a little bit more after 6 years, even based on that average. So I believe that I will have more here. I'm just going to state that. Now, this is part of their, this is without me actually calculating it. This part of the conversational piece they want to have is how exponential functions dominate linear functions over time. So my account will likely have more after 10 years. So keep in mind that we probably have about the same amount after 6 years. We probably have about the same amount after 6 years. And my account balance is growing faster than my friends even after the 6 years. And will continue to grow more thereafter. Okay, if you wanted to do a true comparison though, we can go ahead and go to the graphing calculator and take a look. So we can do y equals, this will be me, 300 times 1.05 to the x power, and then my friend is 10x plus 340. I totally missed the x for mine. Hold on, 340. Okay, I totally have to change my window as well. The smallest y value I really need is 300 actually. And we saw the numbers go up a little bit. Let's go up to like 700 and see what's going on there. Let's do this for 10 years. And let's take a look at, I'll let my friends be bold. But let's see these two equations. Here's mine. It's going to exponentially increase. There's a curve there. You just can't see much of one. And there's my friends. So you can tell mine's slightly curving. Maybe you can't. Let me shrink this. It looks like I don't need to go to 700. Let's go to like 550. So there's mine again. A little bit of a curve. Hopefully you can see it. My friends will be linear. But you can see that after, this is 6 years right here. I already have more even after 6 years, but I'm taking off more so. I just have a greater rate of change. $10 per year starts well for the first 5 years, but I started with more money, right? But the other one thwarts it. It thwarts it. Okay, let's move forward. 3 more sections. Section 6.4 is solving exponential equations. Now, solving exponential equations has a lot of things that go on with it that are different from what we did on solving linear equations. But the thing is to get x by itself ultimately and to get it into its linear equation form. Your goal is to get matching bases if you can. So this example is a really good one as far as how we have to do a matching base set. 1/9 equals 3 to the x plus 6 power. If I can make this 1/9 turn into 3 to some power, I'd be well on my way because I can now have bases match and then set the exponents equal to each other afterward. And 9 is 3 squared. So 1/9 is 3 to the negative second power. That's how negative exponents work. If 3 to the negative second equals 3 to the x plus 6, the only way this is possible is if negative 2 equals x plus 6, because the 3's are the same. So we set negative 2 equal to x plus 6 and solve for x as you normally would. X is negative 8. They don't say check your solutions, and I don't intend to. But let's see what kinds of questions that they give us. Maybe there are special cases like no solution, things like that. All right, number 15, we have 5 to the x equals 5 to the 3x plus 2 power. Very basic one in that, or minus 2 power. Very basic in that the 5's are already the same. That means we can set the exponents equal to each other right now and solve. No, I'm not dividing by 5. I'm simply ignoring the 5's. I'm taking the logarithm of both sides. You won't know what that means for a couple years. Subtract x from both sides, add 2 to both sides, divide both sides by 2. You get x equals 1. Okay, number 16. 3 to the x minus 2 power equals 1. Now, this is kind of I won't call it a special case one, but this is one that even we didn't get to run into in the section outside of one of the more special problems. And they say, what case would this be possible? This is really one to think about hard. You have to rewrite 1 as 3 to some power. 1 is any base to the 0 power. So I can rewrite this with any base that I want. I want to rewrite it with a 3. 3 to the 0 power. If I can make this thing 3 to the 0 power here, I would get 1. So I need x minus 2 to equal 0. I like that the question's on here. I wish that they had at least one of those in the section. In the set. You add 2 to both sides, you get x equals 2. Okay, number 17. Oh, 17 is a special case, however. On number 17, let's think back on our graphs, the range values, the asymptotes that I would draw. Is it possible for me to raise a positive number to some power and get a negative value as a result? No. You can't even get 0 as a result. You can get 1 by raising to the 0 power. You can get fractions by raising to the negative exponent. You can't get negative things right here. That's just not going to be possible. I can't rewrite negative 4 as 6 to some power and make it work. There's nothing there. I'm just going to say no solution straight up. If we did like a solving by graphing, we would see that these never intersect. This would be some exponential function here for the 6 to the power, and this would be negative 4, and they just would never intersect because this one has the asymptote. So no intersection, no dice, move forward. Number 18. Okay, number 18 is pushing us to solve by graphing. Maybe they wanted us to do that on number 17. They just didn't give us the instruction, so I'm telling you straight up, this is what the graphs would just kind of look like. Number 18 is really giving me that push, though. That's because we have exponents. I say this a lot. Variables in the exponent. I got to say that correctly. I was going to say exponents in the variable. You have variables in the exponent, you have variables on the ground. So this is one where I'd much rather do a y equals this and y equals that, graph them, and figure out what to do with it. Now I'm going to graph using the calculator, actually. This is not a fun one to do with a graph on your own, and I want to guarantee that I get a proper value out. So allow me to please sketch these two. Let's get rid of this guy and do y equals, and use parentheses around this, but 1/3 to the 2x plus 3 power. Use parentheses around the exponent as well when it's two multiple terms. And y equals x plus 5. Okay, let's fix our window. It's probably going to be something pretty small here. Maybe I made it too small. We'll see. Oh, you know what? I did make it too. Wait, x plus 5, x plus 5. It would go, oh, perfect, never mind. Okay, there's an exponential curve that does that. It is a decay curve, and this one, x plus 5, boom, like that. Looks like it's intersecting at x equals -2, and I think we were so lucky to see integer values previously where they intersect here. Yeah, x equals -2. Now, as a system, it would be -2, 3, but this original thing wasn't a system. So here I just get to say x equals -2, and I'll even bring the graph over to show that one. But there are the two where they intersect. Let's hope not all these are special cases here on out. I'd like to do some more kinds of questions that we had from before. Okay, number 19. Yeah, this one I'm not going to use a calculator for, now that these are both in the exponent. So, you could. 1/16 to the 3x power, this one's kind of a crazy question though, equals 64 to the 2 times x plus 8 power. Now, my basic goal here is to, again, get your bases to match. And the number that calls out to me is 4 as a base. I can do 4 squared to get 16 and 4 cubed to get 64. Now, you could also do 2. 2 to the 4th is 16 and 2 to the 6th is 64. But those are bigger numbers. I did that once, actually, during that section for a problem with probably using the number 16 and 64. I'm going to leave it. 8 is not a base that can raise to get 16, just 4. Now, 1/16 is 4 to the -2nd power. Keep that in mind when you're doing this. And then 64 is 4 cubed. Now, please use parentheses around this to begin with. There's more to be had. First thing I'm actually going to do, guys, is I'm going to distribute this too. I get 2x plus 16 up there because there's actually more distribution I got to do in just a moment. And that is because when you do a power of a power like this, the exponents actually multiply. So these multiply and these multiply. This has to multiply by distribution. So, -2 times 3x is negative 6x. And over here, 3 times 2x is 6x as well, is positive 6x, and then plus 48. The bases now truly match. I arrived toward the bases matching component here. Now they actually truly match. We can set the exponents equal. So we get negative 6x equals 6x plus 48. I like to make my variable terms positive, so I'm going to add 6x to both sides and subtract 48 from both sides. And then when I divide by 12, you get x equals negative 4. So, trickier, a lot to do, but good on the review. Number 20, also of the tricky substance, I suppose, given what we did before. I think number 19 was actually harder, but unless this is a special case. So number 20, we have 27 to the 2x plus 2 power equals 81 to the x plus 4 power. Now, what I didn't mention before was, because I don't know, based on your teacher or whatever, how you learn to know which exponent, what you raise to what power to get what. Do you get to use a calculator? Do you get to use what I call a power table? Do you have to memorize them? Eventually, over time, I think you'll just learn them. These are powers of 3. 27 is 3 cubed. 81 is 3 to the 4th power. I think it's good to just practice them over time and familiarize yourself. Power table, etc. Try and avoid calculator use as much as possible. But I'm matching bases of 3, but I have to do the same thing as I did last time. Multiply the two sets of exponents through distribution. 3 times those and 4 times those. So this will be 3 to the 6x plus 6 power and 3 to the 4x plus 16 power. So now we can set the exponents equal. This will have a solution. I'll subtract 4x and subtract 6 and divide both sides by 2. You get x equals 5. Now, I didn't double check any of these. By all means, go ahead and double check. The problem is these numbers will get so massive, it's almost not worth checking. But 27 to the 12th apparently is the same as 81 to the 9th. Who knew? Those are big numbers. I mean, huge. Your calculator will probably go like, what are you doing? But yeah, really, really big. Okay, after that, guys, we talk about sequences. That doesn't mean they won't have exponential portions along the way, but geometric sequences, arithmetic sequences are, a big part of what we do here on out. Geometric sequences is this entire section. So you'll probably hear a lot of things what we did before, just in a different light. The example says write the next 3 terms of this geometric sequence. So that's all we're going to do. In this geometric sequence, you have a list of numbers. They have a common ratio of 3, 6 over 2, 18 over 6, 54 over 18. That's all 3. So we get to multiply by 3 to get the next 3 sets of terms. They wrote it in a table. I don't plan on writing it in a table to extend it. I'm just going to extend the list like this term, and that term. You can use a calculator as you'd probably need to, but multiply these numbers by 3 and you get boom, chicka, boom, chicka, boom. And you get those 3 answers there. So that is the next 3 terms of that sequence. Pretty basic question with regard to what we can be asked on those. Like these don't ask exactly that. Numbers 21 to 23 say, decide whether the sequence is arithmetic, geometric, or neither. So we possibly will have a case of neither. Explain your reasoning. If the sequence is geometric, write the next 3 terms and graph the sequence. I'm really hoping for a lot of arithmetic or neithers then. I don't want to do the graphs on these. The geometric ones are really weird for the graphs, honestly, because they just get so big that it's hard to get a scale and fit like 3 on there. By the way, this looks very geometric. 12 divided by 3 is 4. 48 divided by 12 is 4. 192 divided by 48 is 4. Because it has a common ratio, it's a geometric sequence. And that's my reasoning. It's geometric because it has a common ratio. That is 4. Now I need to find the next 3 terms. The next 3 terms we multiply by 4 each time. 192, I'm going to use the calculator for these. 192 times 4 is 768. That number times 4 is 3072, and that number times 4 is 12,288. Here's what I'm going to do. I haven't used the square graphs yet, right? I've only used the tall ones. So I'm going to continue to use the tall graph here. I hope that's okay. That because I would use the square scaled one on the I would use the square scaled one at the time in this section. But because I'm going off of the same video here, I'm going to use this. The benefit of this, for me, is that I can fit 12,000 on here at 12, whereas the other one would only go up to 10. So this here will be 10,000, and 15,000 up here, and 5,000 down there. X's are going by ones. It's not even X anymore. These are actually N, n and a sub n, but the 7 terms here, they say graph the sequence. Now, I'm actually going to start on the 12,000 up here at n equals 7. It's just easier to talk about where that is. 12,288. It's about 12 and a quarter right there. 3,072 already goes super low right here. Right near 3,000 as well. 768 is already down here. So you can see why I'm really not a fan of like doing these graphs as a whole. 192, already super small. These ones, like, forget about it, how small these ones are. They might as well hit 0. Now remember, n equals 1 is your first term, and also we do not draw the curve, right? This is discrete. This is a discrete function here. But those are the next 3 terms. It is geometric. There's the graph for it, and that's number 21. Number 22. Number 22 has the earmarks of something that you would think was geometric, yet something that you would think was arithmetic at the same time. How come? Well, the geometric has this idea of alternating signs, and that's only geometric sequences can alternate signs, arithmetic sequences cannot. So I know it's not arithmetic because the switch in signs, but it's also not geometric. It doesn't have a common ratio. Pretend like all these were positive for a second, positive 18 and positive 36. You'd be adding 9 each time. A geometric sequence wouldn't have something linear appearing even if it had change of signs. If you truly want to test on arithmetic versus geometric, here's why it's not arithmetic. We do minus 27, and then we do plus 45, and then we do minus 63, and there's no common difference. And then here we do times negative 2, and then here we do times negative 3 halves, and here we do times negative 4 thirds. This is negative 2 over 1, by the way, so you can see how this changes. Negative 2 over 1, negative 3 over 2, negative 4 over 3, probably negative 5 over 4 next. There's no common ratio. So this is a neither case. This is neither arithmetic nor geometric. There is no common difference or ratio. Common difference ratio. Does that mean that I couldn't identify what this pattern is via, like, this would be positive 45, then negative 54, then positive 63? I could write the next 3 terms. I could even graph it, but it's neither arithmetic nor geometric with that in mind. So we're actually done on the problem there. Okay, number 23 also has alternating signs, and it has more of the earmarks of that which is geometric. This one looks to be geometric based on, I mean, I don't know for sure, but the numbers are decaying at, they're slowing up their rate of decay, basically. Now, exponential functions cannot change signs like geometric sequences can. Geometric sequences can have negative common ratios, and it does appear to have, when I look at 15 to negative 3, like it's dividing by negative 5, and I can indeed confirm that these divide by negative 5 to get there. But we don't speak in terms of division. We speak in terms of multiplication. So times negative 1/5 is actually what we're saying here. That is the common ratio. This is a geometric sequence, which also means I have to write the next 3 terms, and I have to graph it. So this is geometric. So nothing was arithmetic in this set, but this is geometric. This has a ratio, common ratio of negative 1/5. So the next 3 terms, boom, 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 we have to multiply by negative 1/5 again. I get positive 3/5. And then negative 3 over 25. And then positive 3, they change signs, positive 3 over 125. 125, like so. So those are the next 3 terms, and of course we have to graph these. Now, this is a weird graph. I do use both the positive and negative sides of this thing. 375. What multiple could I go by to make this thing best for myself? The multiples of 75 would be too small. 50, 350? Wait, 20, wait. Just 100. Let's do 100. 200, 300. 375 would fall off the map a little bit, but at least it gets me the right idea of what to do. And then I think this is my best scale given what I have. And again, I am using the tall graph here. So 375 would be, this is like 20, 40, 60, 80. So 20, 40, 60, 80. So 75, 375 is about up there. And please count that point. There it is. That's about our 375. Why not? Negative 75. See, it already goes down to this amount. This is when it equals 2. So 60, 75. 70, 75 is probably about right there. 15, well, this is 20, so 15 is 3/4 of the way up from there. And then -3, these ones get super small here. You won't be able to tell what's what at that point right there. So it gets super small. Deal with it as you may, as you will, and we got it. There's the graph. Best I could do. Okay, no more graphing, at least for these next three. Write an equation for the nth term of the geometric sequence, then find a sub 9. Now, this sounds like writing the explicit rule. It's a phrase that we technically don't hear from the book until section 6.6. Of course, I say it out loud all the time. I probably was saying it back with arithmetic sequences. The explicit rule for these things is as such: a sub n equals a sub 1 times r to the n minus 1 power. Start with the first term, multiply by the common ratio one less time than the term we're looking for. So, our first term is 1. Our common ratios, you can probably tell, is 4. So our equation for this one will be a sub n equals, we start from 1 and we multiply by 4 n minus 1 times. I'm going to write that as just 4 to the n minus 1 power. Kind of easier that way. Now we also have to find a sub 9. A sub 9, we start from 1 and we multiply by 4 8 times, 4 to the 8th power. Because 1 is the first term, the 9th term is 8 away from it. That's why we multiply by 4 8 times, not 9 times. And 4 to the 8th is 65,536. So, explicit rule, and then answer for the 9th term. And that's what explicit rules are good for, right? Being able to find any given term just by substituting that number in there. Notice I did 9 minus 1, but I still used the 9 to get the answer. Number 25, and by the way, all these are geometric sequences. We don't have to bother testing whether it is, so once I know the common ratio, I'm all good to go. This one has an a value, or a sub 1, I should say, of 5 and a common ratio of -2. So we're multiplying by -2 each time. So this one has a rule, a sub n equals 5 times, use parentheses, -2 to the n minus 1 power, like so. To find a sub 9, we're going to do 5 times -2 to the 8th power. Once again, all these will be to the 8th power, right? We're also 9 minus 1, 9 minus 1. Now, without even typing the answer, I do know that the answer will be negative. Wait a minute. The ninth term. Positive. Okay. How do I know it's positive? I have two different ways I can know that. Number one, the one that I'm really looking at is odd term is positive, even term is negative, odd is positive, even is negative, etc. The 9th term would be positive. The reason I shut my mouth for a second was I was looking at the 8. Like, wait, the 8th term should be negative. But I forgot. It's the 9th term. Odd term's negative. Also, -2 is raised to the 8th power. If you use parentheses, like you should, a negative raised to an even number will turn positive. Times a positive is positive. So I expect a positive answer. I'm stating that because if you mess up on your calculator by doing this part, by not using parentheses properly, make sure that you force it positive. So I'm getting 1280, and that should be the 9th term of this sequence. Positive 1280, like so. Okay, let's do number 26. Also geometric, but in its own way. What is that common ratio as the numbers shrink? It'll be some sort of fraction. It's not what we divide by, it's what we multiply by. Your best case for getting your R value here, I got a first term of 486. My R term, let's just use these two numbers, 18 over 54, and try and reduce that. We can divide them by 18, and we get 1/3. So you get an R value of 1/3. This is a sub n equals 486 times 1/3 to the n minus 1 power. Now the interesting one about this for me is that this answer will likely be a fraction. Your calculator will likely go to decimal form. So I'm kind of an in-between on how I'd want to go about this recursively or calculator-wise, because I do not want to write a repeated decimal. So as far as my a sub 9 goes, I would be doing 486, and please, again, use parentheses around this, 1/3 to the 8th power, 9 minus 1. So if I go to the calculator and do this, it would start off with a decimal answer, at least mine will. 486 times 1/3 to the 8th power. It's going to give me this. Crazy looking number, but I want to write the exact answer. So I do have a fraction button to convert to, and this should be able to do it, 2 over 27. So I do get 2 over 27 as the answer. That's one way to do it. We're going to talk about recursion coming into the next section, But recursion says use the, just like how we found the second, third, and fourth terms right here, times -1/5, times -1/5. We can do that several times over until we get the ninth term. So like the fifth term would be 6. The sixth term is 2. The seventh term is 2/3, multiplied by 1/3. The eighth term is 2/9, and the ninth term is 2/27. So you can see I still get that by using recursion. Not too bad. Really, I didn't have to use a calculator to get any of those things right. Just by dividing by 3 or multiplying by 1/3, and we still get there. So just don't write the decimal version. I think that's the big take-home message I want to state on that. Okay, let's go to last section, 6.6. How long have we gone? We reached the hour mark. All right, section 6.6, recursively defined sequences, and we still have 7 problems to go. We got to start with the example even. It says, write a recursive rule for the sequence here, 5, 12, 19, 26, 33. It appears to be arithmetic in nature given that we have a common difference of 7 as we increase the number of terms by 1. A recursive sequence basically takes the previous value and it says add 7 to the previous value. That's what says a sub n minus 1. If this was a sub 3, this is a sub 2. To find the third term, take the second term plus 7, things like that. So to write the actual sequence itself, what we're in essence going to do is, give me a second, I'm trying to get my tool, is identify what the first term is, and then also write what we're going to do from that first term onward. For any other term afterward, take the previous term and add 7. So that's what it is here. For a geometric sequence, we would do times r, but we're going to write recursive rules that way. Some of them will be special cases. It depends on what we have. So let's start with number 27, where it says, write the first 6 terms and then graph the sequence. So graphs come back. This first one appears to be an arithmetic sequence given that it has a common difference. The first term is 4, common difference is 5. Now in a slowed down version of the problem, we would say, hey, the second term is the first term plus 5, which is 4 plus 5, which is 9. And the third term, and I won't slow down like this for any other problem, for any other arithmetic problem, is the second term plus 5, which is 9 plus 5, which is 14. You can see kind of what's going on there recursively. And I mean, listen, we did the recursion thing before, much faster than this. I want to just explain why the equation works the way that it does, how this thing states a sub 5 is a sub 4. That's the a sub n and a sub n minus 1. So that's why this thing does what it does in explaining it. And this is really our mindset. This is how we tend to think of the patterns. We just don't really write this out formula-wise like this. So these are the first 6 terms here. We have 4, 9. See, this is what I would just do. Plus 5 is 14. Plus 5 is 19. Plus 5. Plus 5. So there's the first 6 terms. And then they say graph the sequence. So I'm still just going to use the tall graph, given that I've used it the entire time. I think it's served us pretty well. If I go by 2s, then this would actually even work out for us well. 10, 20, 30. Even though we had some odds along the way. First term is 4. Go by 2. So 4 and then 9, halfway between 8 and 10. And then 14. It's kind of up 2.5 over 1. Up 2.5 over 1. Up 2.5 over 1. Up 2.5 over 1. So there's the graph of this one. It's an arithmetic sequence. You don't connect the dots. It's discrete. And it would keep going. But we're done there. Number 28. On number 28, we have actually a geometric sequence. If you can tell, it's now the previous term is multiplied by something that would represent a common ratio. So a sub 1 is -4, and then the rule is you take -3 times your previous term. So I'll do the same things I did before without that middle step. I'll just say a sub 2 is -3 times -4, boom, which is 12. And this way you can see all the calculations as well. So now -3 times 12. It's just -3 times the previous number. -3 times 12. And then -3 times -36. And then -3 times 108. And then -3 times -324. So sign changes. Ahoy. That's what, 972. So 972, this one probably harder to fit the points. This one, I don't think I benefit as much from using the tall graph. If I went by, I could do 300s. Let's see, 300, 600, 900. I was thinking of just making this be 1,000 here, but that would really cripple what I have. Given that I have to go both positive and negative as well, this is probably best. Now, what does that mean? Each of these are 60. So 60, 120. That's the only problem is it's going to take me a while to kind of come up with what these ones are, given that. So 972. This is 960. 972 is another 1/5 up of another 60. 12 is 1/5 of 60. So about 1/5 up right there. There's my 972. Oh, that should be the a sub 6, huh? So I got to move that thing way over here. 3, 4, 5, 6. There we go. We got it. All right. Let's just start with 12. -4. -4 is a really small guy. It's barely even going to be visible there. So right there. 12 is at least 1/5 of the way up to 60. -36 is a little bit past halfway to 60. So I'd say about right there is pretty good. 108 is between 60 and 120, closer to 120. Well, it's 1/5 of the way from 120. So at least I'm understanding my own graph with this. Hopefully you are as well. -324. That's -320. It's a little less than halfway between that and -360. So about right there. And then it shoots up like that. So actually not bad. I did pretty well with that, all things considered. The next one, also a geometric sequence because we're multiplying by 1/4. So number 29, we have a sub 1 is 32. And the next term is 1/4 of the previous term. This time I'm just going to write the list straight up as we multiply by 1/4. Multiplying by 1/4 is also dividing by 4. So that helps me for the first couple. Divided by 4 is 8. Divided by 4 is 2. 2 divided by 4 is 2/4, but that's also 1/2. It's at this point that you really probably just want to say times 1/4 times 1/4. 1/2 times 1/4 is 1/8, and 1/8 times 1/4 is 1/32. So there's your first 6 terms, and as a graph, I can probably scale these by 2s again, given that I would get 32 up near the very top. So it looks like the tall graphs have really benefited for me, as I have 10, 20, and 30. So 32 is right up here. We're going by 2s. 8, and then 2, and then it shrinks quite a bit. 1/2, this is 1. 1/2 looks like 1/4 of the way, and then, yeah, pretty small there. Like 0, pretty much all I can do with it. There's the shrinkage on number 29. Okay, 4 more questions. Let's do this round of 3 first. Write a recursive rule for the sequence. So now we're doing opposite of what they did, and we have to come up with, based on the case of what it is, arithmetic or geometric, maybe special cases. But we have 3, 8, 13, 18, and 23. We have to identify 2 things in this. First of all, the first term. A sub 1 is 3. And literally, that's a part of our rule. We actually write what the first term is. Now, you can see there's a common difference of 5. Given that we're adding 5 each time like that, then we're going to state it like this. We literally just said what we're going to write. We're adding 5 each time. We take the previous term and add 5 to it to get the value of the next term. That can be our recursive rule like that. Perfect. Wow, straight up. Number 31. Number 31 appears geometric in nature, given that we're doing what each time from one value to the next? Multiplying by 2. So 3, 6, 12, 24, 48. And so on. The first term is 3. And if you saw me do this in the section, I sometimes write this differently than what I'm saying right now. I want my comment to look different from the 1, and I already did. You take the previous term times 2. You're doubling whatever the previous term is, like that. But yes, you do note what the first term is on each of these. Number 32. 32 is probably one of these special cases. Now, you have to kind of look hard about what this thing is. They tend to do kind of the same thing over and over. It's like take the previous 2 terms and do something with them to get the next term. And to me here, it looks like a sum case here. I tend to show it like this. These 2 terms add together to get the next term, right? 7 plus 6 is 13. 6 plus 13 is 19. 13 plus 19 is 32. And this would continue. So we're taking any of the previous 2 terms to get the next term. So this time I'm actually going to write the rule first here, that to find the value of some term, I take the value that's 2 terms before and add it to the value that's 1 term before, like that. Now the first term is 7 and the second term is 6. We would need the first 2 terms of this to be signified for us to actually begin this. Otherwise, we wouldn't know how to get the third term without the first and second terms. So that's the rule on that, and that's what we use, and that's how we go. We have one last question here. It says the first term of a sequence is 8. Let's kind of write this as information. The first term of a sequence is 8. Each term of the sequence is 5 times the preceding term. That's a common ratio. Graph the first 4 terms, write a recursive rule and an explicit rule for the sequence. And I do believe we had to do these for our sets. Let's first write the list. First 4 terms, so 8 times 5, 40 times 5, and 200 times 5. Okay. So graphing these, I don't benefit as much from the tall graph, given that I probably just want 1,000 to be right there. Is there a way for me to hit 1,000 a little more specially? Probably not. Not in a decent way, at least. That'll be my 1,000. Unfortunately, the other numbers will be very small as a result. So the fourth term is 1,000. We have 200, 100, 200 right here. 40 is fine. These aren't bad. 8 is just kind of small. So 8 is all the way down there. 40 is halfway, or less than halfway between 0 and 100. So there's the graph, excuse me. Don't want to cough in the mic. The recursive rules we just talked about on these things here. You take the 5 times the previous term, and then, of course, we have to note what the first term is. This is how I tend to write them. Oh, and by the way, the first term is 8. So we'd write it like that. The explicit rule is what we did before, the a sub n stuff. You take the first term times 5 to the n minus 1 power, and that's what that would look like. So those are both of those, and we are squared away. That's it. Guys, that is the review. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Coming up next is the Chapter 6 test and cumulative assessment, where we do everything from Chapters 1 through 6 in about 10 questions or so. A lot less teaching, more doing. They can have tricky questions. I'm prepared. I'm ready to go. I hope you are as well. Thank you so much. Take care. I'm going to see you in the next one.